All right, okay, let's get started. So as a recap, last time we went through some of the storage technologies, right? And so we talked about, basic chemistry. We talked about different types. We talked about degradation. We talked about lifetime and sort of the different application for your storage. So in this class, we're going to take a look at about the operations of storage. So if you're given a storage, right? So how would you best make use of the storage or of the battery? So there's a lot of different technologies. There are sort of different applications. So some of the some of the applications are clear. Some of the applications, for example, are backup. So backup meaning that you care about your power supply, you care about a reliable source of power supply to act as backup when the grid goes down. That's, for example, UPS. Right. So we have backup. The backup is one option. Another option for storage is essentially you can think of not using them as for backup, but using storage to make money, right? Or a commercial application of storage. Right? So make profit. So it turns out the consideration for these two kind of things are different. Okay, so there's different considerations for different applications. So if you first, for example, if you like backup, so if you use backup, well, so today where you find backup is mostly in computing. This is data centers. Okay. So sort of the big source of backup storage we have our data centers. Right. So because data centers, what they really care about is maintaining the computing load, maintaining their quality of service. So you use batteries to back up essentially this whole data center. Okay, you back up data center. So for a data center storage, right? So for a data center storage. So remember when we covered it, we said there was a power capacity and energy capacity for a storage, and these two do not have to be the same number. So if you are a data center and you're buying storage, you're using battery storage for backup, what should the power capacity be? Let's say you're operating a data center and whenever we build a data center now, we have to build associated storage with it. Remember what the power capacity is? So how will you design the storage? What kind of storage would you buy? What is the power capacity and what is the energy capacity? So if you have, let's say, a 10 megawatt data center, then what is your power capacity for that data center? How will you design it? Okay, so if you have a data center, then the power capacity, this be equal to the peak load. Okay, so a 10 megawatt data center, for example, will have a 10 megawatt power capacity battery. Okay, so what this means is the battery can go from 0 to peak load, very, very fast. So you're not limited by power. This makes sense because if the grid power fails, you want the storage to kick in as soon as possible, and possibly when the data center is operating at peak load. Okay, so you want these things to happen. How about the energy capacity? Right, so how long should the battery operate? Let's say the power fails and your battery kicks in. Right, so how long do you think the battery should go? Okay, so I have a 10 megawatt data center. My battery is 10 megawatts. I said the power fails and the battery takes over. But there's finite amount of energy, right? Energy is power times time. So then what is the amount of energy I should have in my battery, or how should I size a battery? Any ideas? So, right, so the cost is determined by both power and energy. So, having both to be very big may not be very cost efficient. In this case, what should it be? What should any ideas what the energy capacity should be?
Could it be enough to successfully end all the tasks and shut it down?
You can't do it that way, but that may take a big battery. You can't do it that way. So what we actually do in data centers, energy capacity is roughly 5 to 10 minutes at peak power. Okay, so it's a very large battery in terms of power capacity, not very large in terms of energy capacity. The reason that you only need 5 to 10 minutes is this fails over to conventional generator. So most likely a diesel generator or natural gas if you have a big plant. So if you think of a diesel generator as, since a generator takes about 5 minutes to actually, 2 to 5 minutes to turn on for a generator. So you use the battery basically as just a fail over, right? The grid power cuts out, you turn a generator on, that takes several minutes. So at that time, the battery is providing all the power for the data center. Once your own diesel generator turns on, then you can stop using the battery and hand it over to the diesel generator. So this is for the backup consideration for batteries. Okay, so for this kind of application, right, for this kind of backup application, then the issue, most of the issue is how you size a battery. So sizing the battery is a main issue. But once you size the battery, using the battery itself is actually quite straightforward. So it keeps the battery charged at full. If something happens, discharge the battery. Once the power from outside source comes back online, charge the battery while you're at it. Okay, so this is, so then sort of maintain a full or close to full right? So the goal is just to maintain the battery to be fairly close to 100% SOC. Maybe not exactly 100 for lifetime reasons, but very close to it. You want a full battery that can kick in. So the difficulty, mainly challenge, is how you size the battery. Right? So do you size it to peak power? Do you size it to 80% of peak power? Do you size it to do you buy 2 batteries? That's 150% of peak power for redundancy on this kind of issue. Okay, so most of the challenge here is the layout and sizing of the battery. So here the focus is on the layout. Right, so how many batteries do I have? Is it one big battery or 20 little ones? Right, which one is better? And sizing, so how big should they be? Now, what kind of power should they carry? What kind of energy should they carry? So this is similar, for example, sort of a new, I guess not a new application, but an application we're seeing a lot more as we're sort of a large growth of utility backups. So this is more on the side as where if you're utility, you're also starting to use battery as a backup. So for obvious reasons, you don't want to lose. So if you lose power, if you have a battery backup, that give you some margin for operations. Okay? Right. So this is the operation here is not not terribly hard. Like once the power is off, the battery knows what to do. And so it's more of a planning problem than operation problem. Where we see more operational problem is profit making. Okay, so this is basically move energy around in time to make money. Okay, so this is basically what when you try to make profit, right? So you buy a battery, your goal is not necessarily, right? You're not a utility, you're not a data center. So your goal is not necessarily to provide a backup for any application. Your goal is just to say, okay, can I make money? Can I make, I want to buy a battery, I want to invest in battery, can I make money out of this thing? So the reason you can move energy around in time to make money is basically arbitraging price. Right? So electricity price is not constant. Right? So the electricity prices are not constant in time. Okay, so every hour it differs, hour to hour. Especially when you're in a big market, right? When you're in a big market, prices can change quite quickly. You can normally you can observe several spikes in pricing over a period of time. So the idea is if you can basically charge your battery when the price is cheap, hopefully negative, and then discharge your battery when the price is very high. Okay, so then you make a lot of money out of this thing. Okay, so this is sort of operation. So then the sizing here is important, but sort of it's a lot of times depending on your budget, right? How big a battery can you afford in the system? And here the operation matters more. Because now you're controlling the battery is not a trivial question of when to charge to full, and how much to charge and how much to discharge. This is a less clear question than we are using as a backup. We're using a backup basically you maintain it full, then discharge when you need it, and then charge it back when you don't. Here is less trivial. Here is less trivial. Because if you're trying to time the market, trying to time the price, then if you don't know the future price, then this is actually quite difficult to do. It is quite difficult to do. So this is profit making is more where the operation matters more. So for us, we'll focus on the profit making case. Because it turns out to be, at least for the level of this course, is technically a little bit more interesting. Whereas for backup, there's not much to say. We just buy the battery up to your peak load and just leave it there. Whereas here for the operations, there's more interesting things. So also give us a chance to look at markets and other, look at markets basically in the system. Okay. Any questions about this? So do you think you can make so for a lot of battery operators, do you think they make money in the market? Are we very successful in using battery making money? Currently, let's say. Right, Nathan says no in chat, and this is essentially correct. It's actually quite difficult to make money using right now. If all you're doing is to say, I want to buy a storage, I want to put it somewhere in the system, I want to make money using time arbitrage, that's actually pretty hard. So you're better bet to just bet the stock market. You probably make more money that way. Right, so using storage is really difficult. And we'll go through the market, electricity market. We'll see how it works. Then we may or may not get to it for this lecture, but we'll see. If you put a battery in there, you can save. You can have a little bit of profit, but not too much. And we'll cover the reason why. And go into the future and how will you operate this and try to make more money. Yeah, try to make money this way. Okay. All right. So we'll do a very quick look at the power system market. Okay, so this is really a sort of econ 101 type of market, and the actual markets we have in our system are a lot more complicated. Okay, it's a lot more complicated than what I'm going to say in this class, but this work does get a fundamental idea across how the market works. Okay. So market, right? So the basic idea of a market is to provide a place where you can achieve an equilibrium between supply and demand. Basically, you have something to sell or you want to buy something. A market is really a place to exchange. Okay, a place to exchange. And you can think of a role of the market. One of the fundamental roles of markets is to do an efficient resource allocation. So that's one sort of design goal we have for market. We have some resources, right? One is, I said, this is using sort of selling apple as an example. I have some apples. Some people have some apples. Some people have some money. So an efficient allocation, meaning matching the buyer to the seller and agree upon a price. Okay. So our markets is something called a spot market. Okay, so most time we'll be talking about spot market. A spot market is really something that for a single commodity, there is a single price, right? Or we're using price to represent the exchange of goods. Okay, so this is a spot market. And if you have a commodity, so it doesn't matter who's selling it, who's buying it. If a single commodity, then the same price. Okay, so this is commonly what happens in commodity markets, commonly happen in stock markets, where it doesn't matter who's holding the stock. On the sell is the same price for everybody. Okay, so this is what I mean by spot market. Same thing for electricity. Right now, the market is designed as if you have a megawatt of power, then there's a price associated with it. We do not yet distinguish between the sources of power. Okay, currently there is not a way to say, for this power generated from hydro, from wind, from solar, from coal, from nuclear, can you differentiate them? Can you sell them at different prices? We don't have a way to do that. Okay, so that's not something we can do, and there's not, it's unclear whether even this makes sense or not. Okay, so if you're saying, oh, I buy all my power from renewable resources, that may not be technically feasible. At least we don't have a market for that. And so for now, just remember the market you can think of as a single commodity. Doesn't matter where it comes from, is sold at a price. And the way it works is quite simple. It's basically to say that if you're a consumer, if you're a demand, then your willingness to pay, the price you're willing to pay, drops as more and more quantity is offered to you. Okay, so this is what a common assumption in economics is. In this case, apples. So the more you can buy, the less price you're willing to buy them at. Okay, so one, you may be willing to pay a lot more money. But if I offer you 10, by the time you get to the 10th apple, you may not be very interested anymore. Okay, so the price drops. And the demand curve, this essentially sets up what's called a demand curve. And we have a demand function. The demand curve is really a function that relates quantity to price. Okay, so pi is the price, Q is the quantity you're willing to buy, right? So this is interpret that at a given price, the amount of, the amount that you're willing to buy. Okay, this is sort of what this demand curve is. So this is viewing price as X variable, quantity as a Y variable. You can of course turn this around and think of the inverse demand curve. This is price as inverse of quantity. So given quantity, this is the price I'm willing to pay. So demand curve really what we assume is this is monotonic decreasing. Okay, so the more stuff you have, the less price you're willing to pay for them. Okay, so this is our assumption. Any questions about the demand curve? Okay, so this is our demand. Then there's so the slope of the demand curve is something called elasticity, right? So this the slope is called elasticity. So what this means is so the slope's high elasticity, then what we interpret this as is this, you can think of this as a non-essential good. It's normally modeling non-essential good. Okay. As my price changes, right, quite a bit, with sort of the slope is close to zero. The slope is close to zero. This means there's sort of very gradual changing price versus quantity. Whereas low elasticity, this is often modeled as essential good. Okay. Meaning this essential good. Right? So meaning that I want this amount, so I don't care what the price is. I have a fixed quantity in mind, and the quantity I want doesn't vary very much. Doesn't matter what the price is. So for electricity, which one do you think it is? Is it high elasticity or low elasticity? Right. So which one? Right. So the electricity, this is electricity. Right. Electricity is if you're a demand, you're basically saying I want this exact amount. I won't care about price. Right? So whenever most of us use electricity, we turn on a light. We don't check the spot price and decide whether we turn on the light or not. We're going to use whatever power we want, and we don't even think about price. Right? That's not even something we think about. Right? So this means that we have a very low elastic good. So you think about what makes high elasticity. Right. So what is what? So for example, the example we use is Apple as fairly high elasticity, sort of very gentle slope. If you like let's say your commodity is Apple, whereas electricity is a very sharp. In practice, we often model as a straight line. It's given quantity, I need to serve that quantity. So more fundamentally, what makes a high elasticity versus low elasticity for a commodity or for a good? So why is electricity? Why is the elasticity so low for electricity? Any ideas? Right? Right? So it's sort of intuitive. It's a straight line, right? It's almost sort of vertical line. But why? Why? Yeah, go ahead.
It's a necessity. Just that people need electricity for things.
It's a necessity, but if you look at something like food, it's actually not a typical type of food. is actually elasticity is quite high. Right, so again, for example, Apple, elasticity is actually quite high. So food is also necessity, right? So for this, we're economically, or you can think of as, this is essential good, yes, but there is also no substitute. What often makes a high elasticity, there's no substitute. You can't substitute electricity, at least right now. There's no, right? So I want my computer to run, I need electricity. There is not a substitute for it. I need power, electric power from somewhere. But this is often when you have high elasticity, you have sort of substitution. You have fairly easy substitution. And so basically meaning you can substitute the good you want. You don't have to have that exact good. You can substitute for it. Okay. Whereas electricity we don't. Right? So our computer doesn't run anything else. It's only electric power it works on. Okay. So this is a issue with this, right? So the hope is when you have some kind of storage or demand response is to make this line not so vertical, right? So if you think about substitutes, if you have we have big storage, then you can think of the storage as a substitute for the grid, right? So hopefully that will flatten out the curve somewhat. So Seth also says people usually don't see the demand cost of electricity. We don't see the demand cost of electricity, but that's often by design. You don't, right? So it's hard day-to-day operation to keep in mind of this cost, since we're using electricity all the time. Okay, so demand response is certainly a goal to expose people to the real-time, cost of electricity. But right, so that's a way to make it more elastic, give people some more choices. Another hope is to use something like storage to flatten this out, because storage, let's say, is a substitute for the grid, or the grid is a substitute for storage. There's some substitution, and then it's more elastic. So inelastic demand really a lot of times makes sometimes makes life hard because it's inelastic. But most times we're gonna still model demand as a fairly inelastic thing. You can think of storage as creating elasticity in demand. Okay, sort of creating. So there's no elasticity that's sort of artificially created itself to make the system more efficient. All right, so price elasticity for demand. So there's a mathematical formula. So this is really a generalization, so we can have it. We're not going to use this very much. So this is called the epsilon for elasticity. And this is basically the rate of change in quantity. So at a point, divided by the rate change in price. So you have this kind of elasticity. Okay. So this is for dimensionless quantity. That is a measure of elasticity if you don't have a straight line. So if we have a generic curve, pi equals dq, or we have generic curve of q equals d pi, then you can figure out this price elasticity. Right? So we are not going to worry too much about it, but there is some rigorous definition of it. And then similarly, you can look at the supply side, right? So we have a demand curve. At the same time, we have a supply curve. Okay, and the supply curve is very similar to what the demand curve will look like, except this will be increasing. So our supply curve will be something like this. Q and pi, something like this. So this models the cost of production. And namely, what measures this measures only the variable cost of production. Right. So the fixed cost is assumed to be built. We don't worry about when we talk about supply curve. So this, for example, is if you have a generator, is the money it took to build a generator and the money took to buy the land and so on. That is a fixed cost. That normally doesn't enter into the demand curve calculation. Because those are already there. So if you have a fixed cost, the fix is already there. It doesn't matter how much you supply. Okay, so the demand supply curve represents the cost of production, for how much it costs to produce some things. And the idea is as incrementally more costly to produce the next unit. Of good, right? So if you have a good you're trying to produce, then it's progressively more expensive, right? So it gets more and more expensive to produce this. Let's see. Okay, so the idea is, for example, if you're building some things, right? So if you have production, then it may start off to be very efficient, to be very cheap to build it, but then gets more and more expensive. So if we have quantity, and here is you have something like cost, then what we have is maybe start cheap, then start to cost more and more, then start to cost more and more. We have this kind of cost structure associated with the supply curve. So then if you look at the supply curve, it's normally something like this. As the price goes up, as the quantity goes up. So it's more and more expensive to supply something. And then again, the important thing to remember is this sort of there is no fixed cost. Okay, so there may be an economy of scale associated with this, right? There may be this economy of scale. It's easier to build a huge factory than build 10 little small factories. That is a fixed cost. This kind of supply curve doesn't take that into account. It assumes the fixed costs already happened. Okay, so it looks like the variable cost. And so for example, a generator, the more power you produce, the more fuel you need. And we become increasingly less efficient once we push closer to the capacity limit. Right? So a bigger plant may be more efficient, but here we're going to assume the plant is already built. Then your supply function is basically cost as S inverse Q, or Q as S of pi. So this is saying, given a quantity, this is my cost or my price. Given a price, this is my quantity. So this is the supply curve. And we also have some price elasticity of the supply. Right? So the supply is not exactly horizontal. It's normally a increasing function. There's some elasticity associated with it. And then to get the market equilibrium, it's really simple. Right? So market equilibrium is basically you cross so we draw the quantity versus price curve. Then let's say you have a demand curve. And let's say you have a supply curve. And then what you get is you basically cross them. And here we're going to call this the market equilibrium. Okay, so this in some sense Q star and pi star. This is the equilibrium, or the point that determines how much good, right? How much quantity we should exchange, and at what price should we exchange them at? Okay, so this is equilibrium. Any question about this? Any question about this crossing? Okay, so this is fairly common. We have seen this. But the question is, why? Why is this point good? I have two curves. I can, of course, cross them. I get a point. But why is this a point that we want to operate at? Right? What makes this a, right? So let's look at one, what makes this an equilibrium? Two, what makes this as a good equilibrium? Okay, so when you design a market, that's sort of the two questions you want to ask. One is this market stable, right? If we get to equilibrium, will we stay at it? Will we stay there, right? Will we want to operate at this equilibrium? Or another question you should ask is, we can design markets, but does that line up with our idea of social welfare or social good? Is this what we want the market to do? Right? And if you work for somebody like FERC, for example, then all you think about is kind of market design. As a regulatory agency, you can impose all different kind of rules on the market. And then when you want to think about it, is can I get a stable market? Can I get a stable equilibrium? Is this equilibrium a good equilibrium in any sense? Okay, so let's look at why is this a stable equilibrium or not? Right? Do we have? Right, so right? So this equilibrium represents our willingness to supply is our willingness to sell. The demand is our willingness to buy, and we cross them. But is this a stable equilibrium? Is this thing stable? So the way to look at stability is to look at this picture, right? So this says that we want, remember our equilibrium at this point in the middle, at this point in the middle. But let's look at what happens when we don't operate at the point in the middle. If we don't operate at the point of intersection, then what happens? So let's say this is our two curves, we have crossed them. But then let's say we start at this point. Okay? Let's say I start at this point. Then what happens to this point? Is this a stable equilibrium? That is, if let's say I'm the demand, right? Let's say I'm the demand, and you tell the demand that you should buy the good at this price. You should buy this much. You should buy at this quantity and at this price, at this red dot, which is not at the equilibrium, which is not at the center, which is not at the crossing point of the two curves. So as a demand, would you want to move away from this red dot? Do you have an incentive to move away from it? Right. So why is this red dot not equilibrium? Why do we call the intersection point equilibrium? Right. If I'm the system operator and I told the demand, hey, I don't want you to operate at the point where you guys cross. I want you to operate at this red dot. Why will you be unhappy about it? Why might you be sort of unhappy about operating at this dot? Okay, so so if you look at this dot, at this operating point, would you have an incentive to move this way? Would you want to move this way? Why would you want to move this way as a demand? Your demand there, right? So the reason you might want to move this way is you look at the supply curve. You notice that the supply, the price of supplying this is a lot less lower than the price you're buying at, right? Which tells you when you want to buy a little bit more, the price you're willing to pay, which is your demand curve, is still higher than the price that the supplier is willing to sell. Okay, so it's beneficial to you, right? You buy stuff if the selling price is lower than your demand curve. That's when you buy stuff. Okay, so if you're operating at this point, you want to move this direction because it's still cheap for you to buy things, right? Remember, the demand curve represents your willingness to pay, right? Willingness to buy stuff. So when you're operating at this red point, your willingness to pay, the amount of money you're willing to pay, is higher than the amount of money the seller is willing to sell. So that means you should buy more, right? You're happy to buy more stuff. You're happy to buy more things. Okay? So you move towards this point. Similarly, if you start here, and what happens is what you hear for the supplier is the amount of money you're willing to sell stuff at is higher than the amount of money the demand is willing to pay. So the demand doesn't want to operate at this point. So it doesn't want to buy this much quantity at this price. So you move toward this way. So it turns out you always move to this equilibrium point. And you stop moving if you're at this equilibrium point. Okay, so this is a notion of equilibrium. As neither party wants to move, wants to get to that point. So this is, okay, so this is called, again, this is called equilibrium, because if you look from a supply perspective or the demand perspective, they don't want to move. There's no reason for them to move. Any question about this? Okay, and this sort of underpins basically most of the US electricity market data, actually. There's this sort of equilibrium notion. The supply has a curve, the demand has a curve, we're going to intersect the curve, and this is a equilibrium point. And if you look at this, as this sort of makes a requirement that one has to be monotonic decreasing, one has to be increasing clear, because you want them to intersect at a unique point. And then it's easy to work with this unique intersection point and interpret this as an equilibrium point. So this is our market equilibrium. And then I want to solve for this is quite easy. You basically, equal supply versus demand, and just solve this curve. You have two equations, Q and the pi. You have two unknowns, Q and pi. You have two equations, the supply and demand curves, and you just solve them to get the point that's market equilibrium. Okay, any questions about this? About this market equilibrium? Right, so this explains why it's an equilibrium. Okay, so this explains why it's an equilibrium. Nobody wants to move. This actually doesn't explain why it's a good equilibrium. Right, so it says, okay, we have no incentive to move. It doesn't say anything about the optimality of this equilibrium. As a market operator, why would you, operate at this equilibrium, right? So let's take our break now, since again, I have to end at 2 today. So let's take our break now. And when we come back, we'll explain why this is a good equilibrium. Okay, we'll sort of define what good means in this context, what social welfare means in this context. And we'll say why this is optimal in the assets. Okay, so let's take a break and we'll come back at 1:26 to go through that. Okay, let's get started again. Right, so before we keep going, so one note as the final is next Thursday, I believe, right? So next Thursday for us. Right, so the format will be very similar to the midterm, covering what we covered in the class, mostly what we covered in the class after the midterm. Right, so although we'll include sort of basic foundational material covered before the midterm. So the length will be similar, the difficulty was similar. So I think most people did pretty well on the midterm. However, if I think a few people did poorly in the midterm. So if you're concerned about that, you should definitely come and talk to me. Okay, right. So once the final happens, then it will be graded fairly quickly. But then changing grade after a submit is very difficult. Okay. So if you have concerns, do talk to me before the final. All right, so any
The final
other?
is a cumulative?
Final is mostly cumulative, right? Because you think about things we cover after the midterm, right? So for example, a type 3 turbine, right? So we'll include things we said about type 1 and type 2. Right? So it's hard to say it's exactly not cumulative. So we won't focus on what we talked about, in the midterm, but you still expect to know the material.
Okay.
Right, so type 3 is basically type 2 with a voltage, right? With a voltage on the secondary side, right? So that is cumulative by definition. And one note is for the final, when you write your answer, please circle your answer. Okay, so grading the midterm most time took to figuring out which of the numbers is the actual answer to the question. Okay, so especially if you don't get the question exactly correct. Okay, then if I cannot figure out which number you thought was answering the question, then it's hard to give you partial credit. And so for the final, it's important to clearly circle which number is the answer to the question being asked. Okay, so that's important. Second is try to write as clearly as you can. Right, so this is take home. There's no reason to save space and write everything on the same page. Okay, so please don't write. There's no need to write everything on the same page, right? So you can write clearly. You don't have to write a lot, but you can sort of write clearly, indicate which question is which question are you answering. This is the final answer. These are the steps that will be helpful in grading.
So what time is going to be open, the final?
Sorry?
What time is going to be open?
Similar to the midterm, like 5 a.m. or something. Yeah.
Okay.
Good morning. Yeah. Yeah, so very similar to the midterm in the format, very similar formatting. So I will hold an office hour during the day for you to come ask questions, any question you may have. Right. Any other issues with regard to the final? Anything you want to see changed going from the midterm to the final? Okay, all right, yeah. So just most important thing, write clearly and circle your answers. Okay, right? Because it happens on Thursday. I have to turn in the grades by Monday, and I have to grade the seminar course as well. So it'll be a lot of grading for me. And if I don't find your answer, I don't find your answer. Okay, so try to indicate that. If you have questions, you need clarifying questions, ask either through email or come to the office hour for the final. Right, so, okay. All right, so let's continue with this, right? So with market equilibrium, it's basically a point when you don't have any incentive to change. Okay, so if you're a demand, you're not willing to pay more to buy more stuff. If you're a supply, you're not willing to make more stuff to sell. You're not willing to make more stuff to sell. Okay, so this is the crossover point, and that's equilibrium. And in the power system, this is normally achieved by this idea of a centralized auction. Okay, so what a centralized auction means for power system is the following idea. So how does it work? I basically have an operator. I have a market operator. So in the power system, the supply and the demand, they never meet, right? They never interact directly with each other in the spot market. What they interact with is somebody called operator. Okay, so that's normally a non-profit neutral party. And what the operator job is to run this auction. So what you do is if your supply, so if your generator, what you do is you make offers. Okay, so you say, I'm willing to produce this much power at this cost, at this price, right? So this is your offer. Then if your demand, what you do is you make bids, okay? So the bids comes from the fact that you go in and you say, I'm willing to buy this much power at this price. Okay, so I have the system operator basically talk to all the generators, say, please make your offers, and talk to all the utilities, say, please make your bids. And what the operator does is assembles the supply and demand curves. Okay. So how it assembles the curves is assembles the curve this way. So if you look at the, let's say we'll call it use supply first. Okay. So the way it assembles supply curve, it goes from the lowest price. So the supply curve is sort of stacking from the lowest price. Okay, so generator A is in a very low price. So you use this generator A first. Generator B is more expensive, C is more expensive, and so on. So you stack up your supply curve this way. This is your supply curve. You stack everybody. Okay, supply curve. And the demand, you stack downwards. You start from the demand that's willing to pay the most. Right? That's willing to pay the most. So you stack them this way. Okay, and then you figure out this as your equilibrium for the point where they meet in the middle. Okay, so this is so-called a centralized auction because you have the operator running this auction, taking all the information, and figuring out the market clearing. Right? It's the operator trying to figure out where the market clears at. Right, so any question about this? Okay, so this operation, this auction, that's actually a quite private auction. That's actually what's the name. Because if you're making offers and bids, you normally have no idea who else is in the system. You just tell the system your information, and then it's up to the operator to assemble this kind of curves. Okay. So this is, for example, is different than say if you're calling an Uber, right? You got to see all the cars around, you got to see this information and so on. This is not. This is just you submit your own information, and somebody will clear this market for you. Somebody will clear this market for you. And so this is quite a sort of a simple, sort of straightforward centralized auction. You don't really need any information beyond what your own supply or demand is. So what this centralized auction does is its job is to figure out the price. So if you remember, this supply and demand curves are made up from many individual, right? So this is made up from sort of many individual participants. You get this, made up from many individual participants. So then the question is, what is the price something called the clearing price. Okay, so the clearing price is the, so we're going to think of this point as Q star. This Q star is not a very important quantity for us, at least if you're a customer. You don't really care about what Q star is. What you care about is what this pi star is. So the clearing price, this is pi star. Okay, so this is what the clearing price is. What this means is a demand let's say demand, I say Q hat, if cleared, pays that Q hat times pi star. Okay, so it doesn't matter what your actual bid is. Okay, you may have very well bidded at a price higher than pi star. It doesn't matter. It doesn't matter. You will basically pay still at the price pi star. Okay, so you pay at this equilibrium price pi star. Then the supply, I say Q tilde, makes or gets paid Q tilde times pi star. Right. So again, it doesn't matter what your actual supply curve is. Okay. You may be this, you may be the first one. So you may have made an offer that is very, very cheap. Right? You may have made an offer that's sort of very cheap, but still you get paid at this higher clearing price pi star. Okay, so you get paid at this pi star. Right, so this pi star is really important. This pi star is a really important number. This is a clearing price. And again, if you remember to the ERCOT or Texas outage when people were paying 9,000, right? When the price was $9,000 per megawatt hour, it was talking about this number pi star. So this is an important price, clearing price. And everything gets exchanged at this clearing price. So the question is why, right? This is actually a choice made by the market operator. Right? This payment scheme is made by the system operator, actually. So there's nothing forcing us to adopt this payment scheme. For example, the European grid does not use this payment scheme. Okay? European does not use this payment scheme, using something else. The US grid or the North American system mostly uses this payment scheme. Okay, so let's see why. Right? So why will we want to use this payment scheme compared to something else? So the idea is basically, if you compare this centralized auction, there is something else you can do. Right? There's something else you can do as something called a bilateral transactions. Most markets actually bilateral, most markets we think of are bilateral transactions, right? So if you want to buy a car, right, you don't go and enter into some central operator, say this is the price you're willing to pay, and the operator gives you a car. Right? You shop around. Right? You talk to many people, you shop around, you figure out what the lowest price is. So that intuitively is more efficient, right? You get a choice to shop around. But in our centralized auction, you don't have that choice. You tell the operator what you want. Operator spits back this pi star to you. Okay? Operator spits this out and say this is your pi star. Now, this pi star normally actually doesn't have much to do with the price you bid at. Right? So why is this good? Right? So why is this centralized auction why does it make any sense? Why from a regulatory perspective, when we want to design a market this way, why not just open the floodgate and let everybody talk to everybody else? Okay. So the idea was having the centralized auction and making all transactions happen at the same clearing price pi star as the following. So the efficient market, basically the efficient market will say that you will have no choice, right? So if you know all the information, you will not have made a different choice. Okay, so what this pi star trying to do is, it turns out what this pi star trying to do is, this gives us an efficient market design. Okay, so gives us an efficient market design. And the efficiency comes from this pi star actually maximizes some quantity. Okay, so it turns out operating or transaction operating or not operating. Optimizes something called a social welfare. Right, so let's define social welfare. So we're going to skip these. We're going to define social welfare. So if you look at social welfare, okay, so what this actually means is the following, right? If you just look at the demand, let's say this is your demand curve and pi star at this point. Okay, pi star at this point. Okay. So then this is your Q star, this is your pi star. So the amount you pay, right, since all demand pays at the same price, so the total amount that you pay out is essentially this, right? Is essentially this much. This is your total payment. This is your total payment. And this is your total payment. Okay. So if this is your total payment, then what is this little piece here? Then what is this triangle area? Okay, so if you make a total payment of Q star times pi star, is total amount that demand pays out, right, to the generators. Then if you look at this curve, this is the same curve draw again. Economic surplus. Right, so if you draw this curve again, what happens is this is again demand. So that's the same curve again, you add to this point, right? Then the entire area under the curve, this entire area under the curve, this is the cost, this is the amount demand would be willing to pay. Because the area under the curve is actually the break-even point for demand. Okay, this is the break-even point for demand. Because if this is your demand curve, right? Remember demand curve meaning you're willing to pay this price at this quantity. Then if you integrate the area under the curve, that's actually the total amount you're willing to pay. Okay, right? So if you pay this amount as a demand, you would have been happy because you broke even. Right? The amount you paid is equal to your willingness to pay. Okay, this is your break-even point. But then if we operate at this pi star, if all transactions happen at pi star, you actually pay less than what you would have willing to pay. okay, you actually pay less. So this is called, if you look at this area, this is called the surplus. Now this is in some sense amount of money you saved. This is the amount of money you saved by operating at high star. Okay, you did not have to pay this entire area under the curve. You only paid a piece of the area under the curve. Okay, so you save some money, right? So this is, you're happy from the demand perspective, right? You're happy from this perspective. Okay. And basically the mirror image happens for the supply side. Okay, so let's look at what happens for the supply side. Okay, so if you look at the economics for the supply, this is surplus. It's very similar because if this is your, say, supply curve, and this is, say, this is Q star, high star. Okay. But if you look at the area under the curve, this is your cost. Okay. So this is actually your, sort of the amount you're willing to earn. Because this represents a break-even point. The area under the curve is again a break-even point for the supply. Okay, this is the amount of money you're willing to pay to make this much stuff. Okay, at this point, you make no profit, but you make no loss. So this is break-even for you. Okay? But then you actually get paid this rectangle, right? That's the Q star times pi star. So this area is actually the profit you make. This is a net profit of demand. Okay, so this is your net profit. And this is your net profit because it's extra money you got on top of your production cost, on top of making back your production cost. So on top of making back your production cost, you made this extra money defined by this region. Okay, defined by this region. So this is a surplus for the demand, surplus for the supply. So the supply is happy because you made some money, right? You made some money. And if you look at both together, then what we figure out is basically, as both from supply and demand, you make some, right? So you operate at some surplus. So your social or global welfare basically comes from this region. Okay, so if you divide this region up, on top of it, this is the demand surplus, defined as the difference between the area under the curve and the payment, total payment. This is the supply profit. Okay. So together, this is the total. This is the social welfare. Okay. So together, there's social welfare. And basically, if you, so the theorem, right? So the fundamental theorem here is if we operate a pi star, this maximizes the total social welfare. Okay, this basically maximizes total social welfare. All right, so if we pay everything, if everything is chosen, all the transactions are clear at the pi star, the clearing price, the equilibrium price, then we basically maximize the area between these two curves. We basically maximize this area. If we transact at any other price, for example, let's say we transact at here or here, that actually does not maximize welfare. So the welfare is maximized precisely when we make all transactions happen and pi star. So this is the economic theory, and this is how price is determined in the system, basically. This is how we determine price. So, and the theory behind it is so there's a good theory behind it if you think about this as a sort of maximization problem. So so supply is happy, the demander is happy. So of course, in practice, whether this makes sense or not is debatable. Okay? So there are, not everybody is happy with this regime, but in the US, it's offered based on this principle. So can you guys think of what Europe does? So Europe does not operate on this principle. Europe does not. Europe does not pay at the clearing price, for example. Any guesses what they do? So Europe doesn't have this idea of a pi star or this sort of clearing price equilibrium. Any ideas what happens there? Or what is the alternative design you can think of? Let's say, so I present to you this idea of we clear the market, we get one price, right? A unique price, and we offer everything done at that same price. Can you think of an alternative to this? Is there an alternative design to this market? Any ideas? Is there other ways we can do this without, say, just everything happens at a single price? Okay, so what Europe uses, so this is EU uses pay as bid. So what pay as bid means is you get paid whatever price you offer or bid at. Right? So this is exactly what it means is pay the offer or bid price. Okay. So Europe does this saying we're not, so what we do is we'll clear the market. Right? We'll clear the market. But this market clearing basically just tells you if you're in the market or not. Just tell you if you're in the market or not. And if you're in the market, if you get cleared, then you will operate at your own, whatever the cost or whatever the supply or demand bid or offer you have made. We're not going to bother with the notion of a clearing price. Okay? So if you're in the market, you do what you're going to do. Okay? So that's Europeans' method. So that method, so there's debate between which one is better. So the US one has, I think, a bit more theory sort of foundation behind it, right? Whereas if you operate in the European market, basically what you do is, you have to guess what the clearing price is, and you want to operate as close to the clearing price as possible. Right? So you don't, in some sense, offer your true cost or you don't offer your true cost. Rather, you guess what is the possible clearing price, and you sort of structure your bid and offer as close to that as possible. Okay, so that's a European model. So in theory, the US one makes more sense. But I think in practice, it's debatable which one ends up working better. Okay, so in practice, hard to say which one is more preferable than the other one over the long run. So that's an open question in market design. Now, do we want to clear everything? Do we want and make everybody operate at the same price? Or is that you should operate at the price you said you are going to operate at? So that's a debate we have. And this debate will get more interesting as we have more and more renewables and distributed energy resources coming to the market. Okay, so that's interesting. Okay. So as we said, so I will stop here today. We'll stop here today. next class will basically put storage and wind into this picture and look at what happens in terms of system prices and see whether, really you can make money as a storage, or actually can you make money as a wind turbine? Okay, so we want to ask all these questions about from an economic perspective, right? Regardless of environmentally as a society, whether we want these or not. The next class we'll look at from economic perspective, does it make sense for these new resources to enter the market as it is structured by what basically I described today? Okay, so let's stop here today, and I will see you on Thursday. Thanks, guys.
Thank you.